Okay, wonderful. Today's date is Wednesday, March 9th. Wednesday, March 9th, 2022. And so I'm going to erase this. Hold on. This is the erase button. Okay, so we're going to write Wednesday. Oops. This is the trick I learned. You have to use this pen and touch with a pen thing, because I was doing with Dr. Richards, and we were using our finger to punch this, and then it still wouldn't work, but you have to use this to punch it, to activate it. So I'll say Wednesday, March 9th, 2022. We're talking about groups. Okay, we're talking about groups. So, oh yeah, let me quick attendance here. All right, so we are, I probably should just do the attendance of the people who are here. So we have Genevieve, Rohit, Bernie. Okay, Bernie's confusing me now, so he's moved. Okay, Richard, Emin, Parker, Pundit, David, Ty, and Shritan. Okay. All right, so a group is a non-empty set and a binary operation called product. Such that there's four conditions. So Genevieve, what would be one of those? Is a non-empty set with a binary operation, and you got four things that have to be true. Closure, right, very good. So we got closure, and that means that A, B, and G implies that the product of A and B is in G. Of course, we say product, but the operation could be addition, but we just use the dot as kind of a universal operation. Okay, and then I see Parker's just dying to contribute to the discussion here. So Parker, what's another quality of groups? Associativity, right. So that means that A, B, oops. A, B, C, and G. Oops. You know what? It's very tricky doing this thing. Okay. A, B, C, and G implies that A product B product C is equal to A product B product C. So this is called associativity. Very good. Associativity. Okay. And number 3, Ty, what would be another quality of group? Yes, it has to be identity. So that means that there exists an E such that for all A and G, A times E is equal to E times A is equal to A. So I'm using some of the notation of mathematicians here. You got the upside down A and the backwards E. So I'm not trying to do that to intimidate you guys. It's just faster to write that. Okay, and then lastly, Shritan, what's the fourth and last kind of quality of a group? Yeah, well, you have an existence of inverses. So each element has inverse. So for every A in G, there exists an A inverse such that A times A inverse is equal to A inverse times A, which equals to E. E is the identity. Okay, great. So you've got to have identity and inverse. So in short, you've got to have closure, associativity, identity, and inverse. So pundit, give me an example of a group. Give me an example of a group. Real numbers under addition. Okay, let's take a look. So we're going to look at example. We're going to look at real numbers under addition. So group is not just a set. Like you just can't say, if I say, give me an example of group, you just can't say set of real numbers. You got to say set of real numbers under something, under addition. So let's take a look. Closure. Okay, is it true that the sum of two real numbers is a real number, Emmett? If I take a sum of two real numbers, is that a real number? Yes, very good. Closure, yes. I'm going to put Emmett approved. Okay, that's like the good housekeeping seal of approval. So Emmett has approved that closure. Okay, what's the, how about Richard? What about associativity? Does that hold? Yep. So that's Richard approved. Because that's something you actually learn in elementary school. I don't know if they use the word associative. The associative property holds. So this means that A plus B plus C is equal to A plus B plus C. So you do what's in the parentheses first. So A plus, because addition is a binary operation. So you can't act it can't act on three things, it acts on two things. So you have to do B plus C first, and A plus, the result of B plus C is the same as the result of A plus B plus C. Okay, so associativity, so Richard approved. And then Bernie, what about identity? Is there an identity that lives in the real numbers? And that would be good. Yeah, so we got identity. And so that is going to be Bernie approved. Bernie approved. Great. So that's notably it's 0. 0 is identity. Okay. And then lastly, I think I called on everybody because Genevieve answered a question. Rohit, did you answer a question yet? Oh, I'm really sorry. Okay. I think Rohit and David did. I want to make sure everybody gets them up. So Rohit, what about the existence of inverse? Is it true that every element has an inverse? Okay. So element is A, what is its inverse? Good. So inverse, yeah. Inverse is, and that is Rohit approved. Rohit approved. So that means that given element A, negative A is its inverse. You know what makes this confusing is because the groups have its own notation, the A to the negative 1. So what we're really saying here is, in our case, that the inverse of A is equal to negative A, because this A to the negative 1 is a notation from group theory, meaning this means the inverse of A. Well, in this case, under addition, the inverse of A is negative A. So it's a little confusing because the operation here is not multiplication. We think of that as multiplication, but it's actually, the operation is addition. So we think of this, that's what we call product. We don't say it's a, so it is a group operation. Okay, very good. Very good. Now let's take a look at some examples that came up last time. So last time, these are some example students through under subtraction. Integers under subtraction. So we have, yes, but when we got to associativity, no. Associative is no because 2 minus 3 minus 1 is not equal to 2 minus 3. So that's not true. So so associativity does not hold. And then someone said, I think last time, they said integers under division. That's well, you could say that closure no, because if I take 1 divided by 0, that is undefined. So closure did not hold. You can't do the, and then I think we have another one. Let's do I don't think this was an example given by a student, but we'll look at non-negative integers under addition. We're going to look at non-negative integers under addition. So non-negative integers means includes 0. So it'd be like 0, 1, 2, 3, 4, 5. So let's take a look. Genevieve, does closure hold non-negative integers under addition? Is it true that the sum of any two non-negative integers is a non-negative integer? So that holds. So this is Genevieve approved. Okay, great. What about associativity? Associativity. So, Treated. Is it? Oh no, David. David, what about associativity? If I look at non-negative integers under addition, how about associativity? Does that hold? Yep, that holds. Yep. Yes. So it turns out that A plus B plus C is equal to A plus B plus C. Very good. Associativity holds. All right, what about identity? What about identity? So, treated? Does there exist identity here? Is it true that there's some special element such that A plus that special element is A? And it's a non-negative integer. Yep. 0. Very good. Yes. So this is yes. So this is Treachen. Very good. So this is 0. So 0. Very good. About inverse. Inverse. So Ty, if I give you an element 5, does it have an inverse? No, because the inverse of 5, it would be -5, but -5 doesn't exist under this world. So inverse, no. There's only one element that does have an inverse, and which one would that be? There's only one element of this set that has an inverse that lives in that set. Don't think too hard. Yeah, 0, right. So 0's inverse is 0. So no, inverse of 5 is not in set. Okay, very good. So on your test, the next time we meet, I'll give you a copy of the abstract algebra test. So on the abstract algebra test, I'm going to say define a group. You know, I'm going to actually set it up for you. Like say, G is a non-empty set, and along with a operation called product, designated by the dot, four conditions must hold, and then you have to list the closure, associativity, identity, inverse. You have to do that. And then I'll say, give an example of a group. And then you have to give an example of a group. Okay, very good. So kind of some basic notation I forgot to mention is I'll say the number of elements in a group, G, is designated by O of G and read order of G. So the order of the group is the size of the group. You could have, and a group can have an infinite number of elements. Group can have a number. Now, when we did our fruit, group theory, the fruit stuff, oh my gosh, it's 101, and I got like 4 minutes left. Okay, so, and then a cyclic group, a cyclic, this is a cyclic group is a group that can be generated by a single element. So you would have like a square, a cubed, and so forth, all the way to an equals to e. N is equal to number of elements in G. So cyclic group is a group that you can find element A. So I can look at a square, a cubed, all the way up to a to the n. And so here the order of G. Ooh. Okay. Order of G is equal to n. Order of G is equal to n. So, and not all groups are cyclic. For example, the Klein-Beer group is not cyclic. So we did the fruit stuff, the group order 2, group order 3, they were cyclic, but the Klein-Beer group is not cyclic, and S3, the symmetric group of degree 3 is not cyclic. And also, if A times B is equal to B times A, for all A and B in G, then we say G is abelian. And if not, G is said to be non-abelian. Okay. Oops, it's 104. I'm going to go over because we actually started at 143, so I should go over a little bit more to like 108. So let's look at the homework assignment. So homework, one of the homework problems was 9A. Let's look at 9A. Show that a group of 3 elements is abelian. Okay, so 9A says show that a group of 3 elements is abelian. So let's list the elements, knowing that one element is the identity. Okay, so that means I got E, A, and B. E, A, and B. I know that E has to be in there, right? E has to be in there. And don't worry, because everything's being taped, or at least I hope it's being taped. Oh no. Did I forget to? Oh, phew. Okay. Okay. I'll post up the. So I got EAV. Okay. Now I know by lemma 2.3.1. I think it's 2.3.1. By lemma 2.3.1. Those are preliminary lemmas. Oh no. By definition. By definition of group, E times A is equal to A times E, which equals A, and B times E is equal to E times B is equal to B. Okay? So now we only need to check we need to check A times B and B times A. Okay. Now, if A times B is equal to A, then B is equal to E. This is by lemma 2.3.2. That's the cancellation. So if A times B is A, then I can kind of cancel out the A's. I get B is equal to E. But this is contradiction because identity is unique. There can only be one identity, and that's just plain old E. I can't have something else be E too. So these are the distinct elements. Or you could say, you don't have to say that, you could just say E, A, and B, they're all distinct elements. E, A, and B are distinct elements. So I can't have B equals E. I gave that it has identities unique, but I may not have to go that far. I could just say E and A and B are distinct, or simply say are all distinct. So B can, and then I note that A times B is equal to B leads to, and that's a contradiction. I can't have that. So finally I have to conclude, that A times B is equal to E. A times B can't be A times B can't be B, so that means A times B has to equal E by closure, right? Similarly, B times A has to be equal to E. And that implies that A times B is equal to B times A. And then I'm done. So I'm done because I've already checked A times, I checked A times E. So basically I've showed that A times E is equal to E times A. B times E is equal to B times, is equal to E times B, and A times B is equal to B times A. There's no other, these exhaust all possible products. So therefore, a group of 3 elements is a group of 3 elements. So I'm just using the properties of groups. So I look at a group of 3 elements. It's got to have an identity. So E has to live in there. So I've got E, A, and B. And then I have to look at A times E is equal to E times A. I know that B times E is equal to E times E. That's all from my definition of a group. That's all from my definition of group. Now I have to look at A times B and show that's B times A. So I have to go through A times B. Well, could it be A? No. If A times B is A, then that means that B is equal to E. If A times B is B, that means A is equal to E. I can't have that. I have to have, these are all distinct elements. There's a unique identity. So finally, I have to conclude that A times B is E. That's my only choice. And similarly, B times A is E. So now I have its trivial group. Now, you have to also show this for a group of 4 elements. And I did it for a group of 9 elements. But because I was a hardcore math person, so I worked out all the possibilities for the 9 elements. So you don't have to do that. You don't have to do that. But try it. And I didn't even give you 9C because 9C says to show it for 5 elements. But it gets more complex. It gets more complex. But you have to think about it. The group of 4 elements, I did it for you in the fruits. And there's 2 non-isomorphic groups of order 4. There's one that's cyclic, and there's one that's the Klein-Beer group. So, okay. I went over. I told you I was going to end early. So you all have a wonderful afternoon. I will take my lecture today and post it up. So we're giving extension on your homework because it was due on Friday, but they're mostly proofs. There's mostly proofs. Give it a try. Don't worry. I'm not going to sock it to you guys. You know, I'm trying to make you successful in this class. I think I may have at most one in the class that wants competition. So that's that will really want to do the homework. But and then it'll give you a little flavor for what it's like to want to study pure math. Because pure math is all about proving things and trying to be rigorous about your thinking about things. So you all have a wonderful day, and I am going to press my button here